time. It's the one thing we all share, yet it remains the ultimate mystery. It dictates the rhythm of our lives, the birth and death of stars, and the fate of entire civilizations. We feel it slipping through our fingers, an invisible, unstoppable current carrying us forward. We talk about wasting time, saving time, making up for lost time, always treating it like a river, flowing from a fixed past, through a fleeting present, and into an unknown future. But what if that's all wrong? What if our most basic intuition about time is just a grand illusion? In the last century, our understanding of the universe has been turned upside down, and our concept of time along with it. Physics has revealed a reality far stranger and more profound than we ever imagined. The comfortable, steady ticking of a universal clock, it doesn't exist. Albert Einstein was the first to shatter this illusion. He showed us that time isn't a rigid, absolute stage on which the universe performs. Instead, it's a flexible, dynamic dimension, intricately woven together with the three dimensions of space to form what we call space-time. Your personal experience of time is unique to you. The faster you move, the slower time passes for you relative to someone standing still. The stronger the gravity you experience, the more time stretches and warps. An astronaut on the International Space Station is literally aging a fraction of a second slower than we are down here on Earth. Time, it turns out, is relative. Modern physics doesn't stop there. When we dive into the bizarre world of quantum mechanics, the very fabric of reality seems to fray. On the smallest scales, the familiar, smooth flow of time dissolves. In some of the most fundamental equations that attempt to describe the universe, the variable for time simply vanishes. It's not there. This has led some physicists to a radical idea. Perhaps time isn't fundamental at all. Maybe it's an emergent property, something that arises from a deeper, timeless reality, much like temperature emerges from the chaotic motion of individual atoms. You can't talk about the temperature of a single atom, only a collection of them. Similarly, maybe time only makes sense on a larger classical scale, but disappears in the quantum realm. Then there's cosmology, the study of the universe as a whole. Our best theory, the Big Bang, tells us that not only matter and space, but time itself had a beginning. Around 13.8 billion years ago, everything we know exploded into existence from an infinitely hot, dense point. Before that moment, the question what came before might not even make sense because there was no before.
Ow.
Time itself began with the universe. And if time had a beginning, could it also have an end? Will the universe expand forever, cooling until a final heat death? Or will it collapse back on itself in a big crunch? The ultimate fate of the universe is also the ultimate fate of time. From the relentless ticking of our clocks to the slow dance of distant galaxies, we are surrounded by the effects of time. We perceive it as a fundamental arrow, pointing us from yesterday to tomorrow. Yet the deeper we look, the more it seems to be a complex, perhaps even illusory, feature of our universe. Is the future already written? Is the past still out there, somewhere? Are all moments in time equally real, existing simultaneously in a grand cosmic block? These aren't just philosophical questions anymore. They are at the very heart of modern physics. To truly understand reality, we must first confront the enigma of time. And our journey starts at the very beginning, the birth of time itself. What is time? Is it a cosmic clock, ticking away at a steady, universal pace? Or is it something much stranger? To find the answer, we have to journey back to the very edge of the beginning, to a moment before even made sense. About 13.8 billion years ago, our universe burst into existence in an event we call the Big Bang, but that name is a bit misleading. It wasn't an explosion asterisk in asterisk space. It was the expansion asterisk of asterisk space itself. Before this, there was no space and there was no time. Einstein's revolutionary theories taught us that space and time are woven together into a single fabric, space-time. So, when the universe began to expand, time was born right along with it. There was no ticking clock waiting for the universe to start. Time itself ignited with the cosmos. This is one of the most mind-bending ideas in all of science. Time is on the stage for the universe's drama. It's one of the main actors. For centuries, we thought of time the way Isaac Newton did, as an absolute. Unchangeable river flowing the same for everyone, everywhere. A second on Earth was a second on Jupiter. Simple, right? Well, in the early 20th century, a young patent clerk named Albert Einstein turned that idea on its head. With his theories of special and general relativity, he revealed that time is not fixed at all. It's stretchy. Einstein showed that time is relative. The faster you move through space, the slower you move through time compared to someone standing still. And gravity, he explained, isn't a force pulling you down. It's the curvature of space-time itself. The more massive an object, the more it warps this fabric. And here's the kicker. This warping doesn't just affect space. It affects time. Time literally ticks slower in stronger gravitational fields. So your now is different from the now of someone on a distant galaxy. There's no single, universal present moment. The universe isn't one giant synchronized clock, but an infinite number of personal timelines, all interwoven. Think of space-time as a vast, flexible trampoline. A massive object, like a star or a planet, creates a dip in it. Other objects, like comets or satellites, follow the curves in that dip. That's what we experience as gravity. But it's not just the path of objects that changes. The pace of time changes too. This isn't just a wild theory. We measure it every single day. The GPS satellites orbiting Earth are moving very fast and are in a weaker gravitational field than we are. Their onboard clocks actually run faster than ours. If engineers didn't constantly correct for this relativistic effect, your GPS would send you miles off course within hours. Time's relativity gets even more extreme near a black hole where gravity is immense. As you approach a black hole's event horizon, time for you would slow down dramatically from the perspective of an outside observer. They would see you appear to freeze, trapped for eternity at the edge. But for you, inside your spaceship, time would feel completely normal. Minutes would pass like minutes. This bizarre paradox proves that time isn't some abstract concept. It's a physical geometric property of the universe, as real as length, width, and height. So, if we can wind the clock back, what did time's first moments look like? As we get closer and closer to the Big Bang, the universe becomes unimaginably hot and dense. At a point called the Planck time, mere 10 to the minus 43 seconds after the beginning, our current laws of physics break down completely. This is the frontier of our knowledge. Did time truly start at the Big Bang? Or was there something before? Some theories, like loop quantum cosmology, propose that our Big Bang might have been a big bounce from a previous contracting universe. Others, like the Hartle-Hawking no-boundary proposal, suggest that asking what came before the Big Bang is like asking what S north of the North Pole. The question itself is meaningless because the concept doesn't apply. At that point, time might have smoothly transitioned into a dimension of space. The birth of time remains one of the deepest puzzles in physics. It's easy to think of time as something we just experience, feeling, a memory, the ticking of a clock on the wall. But physics tells us it's so much more. Time is a fundamental component of reality, inseparable from matter and energy. When a star burns, when a galaxy spins, when light travels across the void, these events don't just happen in asterisk time. They are the processes that define time. Without time's forward flow, there would be no cause and effect, no change, no evolution. The universe would be a static, frozen snapshot, a 4D block of space-time with no story to tell. Time is what allows the universe to happen. And yet, after all this progress, the ultimate nature of time remains a profound mystery. Is it a fundamental dimension, or does it emerge from something deeper? Does it flow continuously, or is it made of tiny, discrete ticks, like the frames of a movie? And perhaps the biggest question of all, why does time have a direction? Einstein's equations work just as well forwards as they do backwards. But in our reality, you can't unscramble an egg. The arrow of time points stubbornly from the past to the future. What gives it this direction? Is it a fundamental law of nature, or just an illusion created by the way our brains process information and memory? The search for these answers takes us to the very heart of what reality is. The story of time is far from over. In many ways, it's just beginning. Have you ever wondered what time really is? We think of it as a constant, a steady beat marching forward. But what if I told you that to see the true nature of time, you have to go to the universe's most extreme places? Places where time itself begins to warp, twist, and even stop. Today we're going on a journey to the edge of reality to discover that time isn't just a concept. It is a physical phenomenon that bends under the weight of the cosmos. Back in 1915, when Albert Einstein published his theory of general relativity, it was mind-bending. Proposed that space and time are fused together into a single fabric, space-time. Just like a bowling ball warps a stretched rubber sheet, massive objects like stars and planets warp this fabric. That curvature is what we feel as gravity. But Einstein's theory went even deeper. It predicted that gravity doesn't just pull on space, it pulls on time. This meant that time itself should tick more slowly near massive objects. A clock on the surface of the Earth would run just a tiny bit slower than one high up in orbit. At the time, this seemed impossible to prove. Who could ever measure such a minuscule effect? Well, decades later, we did. And the results didn't just change physics, they changed your daily life. Every single time you use your phone for directions, you're putting Einstein's theory to the test. The GPS satellites orbiting Earth carry incredibly precise atomic clocks. But because these satellites are farther away from Earth's gravity, time actually moves faster for them. At the same time, they're zipping through space at thousands of kilometers per second. And another part of relativity tells us that moving clocks tick slower. So you have two effects fighting each other. The weaker gravity makes the satellite clocks run faster by about 45 microseconds a day. Their high speed makes them run slower by about 7 microseconds. The net result? Satellite clocks get ahead by about 38 microseconds every single day. That might sound insignificant, but if engineers ignored it, your GPS would be off by about 10 kilometers every day. Think about that. Every second, your phone confirms that time is relative, a malleable part of the universe's structure. But if you want to see time truly misbehave, you have to go to a black hole. These are the densest objects we know of, places where gravity is so intense that nothing, not even light, can escape. When a massive star collapses, it can create an object so compact that it literally tears a hole in the fabric of space-time. General relativity tells us that as you get closer to a black hole, time slows down dramatically for you compared to someone watching from far away. From their perspective, you would appear to move slower and slower, until you reach the edge, the event horizon where your motion would seem to freeze entirely. From your point of view, you'd fall in within seconds. But for everyone else in the universe, your fall would take an eternity. This isn't science fiction. It's a verified consequence of Einstein's equations. You don't need a black hole to prove it. 2010, scientists performed one of the most delicate experiments ever. They took two of the world's most precise atomic clocks and placed them at different heights just 33 centimeters apart. One was literally just a foot higher than the other, and guess what? The clock closer to the ground, deeper in Earth's gravitational field, ticked just a little bit slower. A difference in height smaller than your desk was enough to measure the warping of time. This proves that relativity isn't just for cosmic scales. It's happening right here, right now. In fact, your head is aging slightly faster than your feet. It's a tiny, tiny amount, but it's real. Let's go back to that point of no return at a black hole, the event horizon. From the outside, time appears to stop there. But if you were the one falling in, your own clock would tick normally as you crossed it. You wouldn't even notice the moment you passed it. This bizarre paradox, where time can both stop and continue depending on your perspective, is one of the wildest features of relativity. What happens inside? That's one of the biggest mysteries in physics. Einstein's theory predicts a singularity, a point of infinite density where our understanding of space and time breaks down completely. But quantum mechanics, our other pillar of modern physics, says infinities can't exist in the real world. To solve this puzzle, we need a new theory, a theory of everything that can unite gravity and quantum physics. But what if a star collapses and doesn't quite become a black hole? Then you get a neutron star. Imagine the mass of our sun crushed into a sphere just 20 kilometers wide. The gravity on its surface is so intense that time there runs significantly slower than on Earth. Some of these neutron stars spin rapidly, beaming out radio waves like a cosmic lighthouse. We call them pulsars. Their pulses are so incredibly regular that astronomers use them as galactic clocks. It's even more stable than the atomic clocks we have on Earth. By watching these pulsars all across the galaxy, Scientists can measure how time bends and stretches on a cosmic scale, putting general relativity to the ultimate test. Then in 2015, we witnessed something truly monumental. Scientists detected gravitational waves for the first time, ripples in the fabric of space-time itself, caused by two black holes colliding over 1 billion light-years away. These aren't waves moving asterisk through asterisk space and time. They are waves asterisk of asterisk space and time. As a gravitational wave passes through you, it stretches and squeezes the very space you occupy, and time itself oscillates, ticking just a tiny bit faster than slower, in rhythm with the wave. Einstein predicted these waves 100 years earlier, but thought we'd never be able to detect them. Now, we do. Every time we detect one, we are literally watching time itself ripple. All of this might sound abstract, but it has very real consequences. You've probably seen the movie Asterisk, Interstellar Asterisk, where astronauts visit a planet orbiting a supermassive black hole. On that planet, 1 hour equals 7 years back on Earth. That wasn't just Hollywood magic. It was based on real physics. While no human could survive in that environment, the time dilation effect is a calculable result of gravity's immense grip on time. So what does this all mean? From your GPS to colliding black holes, the evidence is overwhelming. Time is not just in our heads. It's a physical, measurable dimension of our universe, one that can be bent, stretched, and even brought to a halt by mass and energy. The ticking of every clock is governed by the same cosmic geometry that holds galaxies together. The deeper we look, the more we realize that time isn't separate from the universe. Time asterisk is asterisk the universe. But this leaves us with an even bigger question. If time can slow down and stop, can it go backward? Why does it seem to move only in one direction, from past to future? That is the great puzzle known as the arrow of time, and we'll explore that next. Why does time only move forward? We remember the past, we live in the present, and we look toward the future. It feels so natural, so obvious. A hot coffee cools down, but never heats up on its own. You can scramble an egg, but you can't unscramble it. This one-way street is built into the very fabric of our experience. But here's the mind-bending part. Physics tells us something completely different. At the fundamental level, the laws governing our universe don't care about the direction of time. So, why do we? Why does time have an arrow, always pointing from yesterday to tomorrow? Let's dive into one of the deepest mysteries in all of science. At the heart of physics lies a paradox. Every major law, from Newton's equations to Einstein's relativity and even quantum mechanics, is time-symmetric. This means they work perfectly fine whether you run them forward or backward. If you recorded two particles colliding and played the video in reverse, the math would still add up perfectly. In the tiny microscopic world, there's no difference between past and future. Yet, when we zoom out and look at the universe as a whole, it's clearly evolving in one direction. It moves from a state of order to disorder, from low entropy to high entropy. This massive contradiction is one of the greatest riddles in physics. If the laws are symmetric, is our experience of time so stubbornly one-sided? The first big clue came in the 19th century from a physicist named Ludwig Boltzmann. He proposed a revolutionary idea. The direction of time is defined by entropy, which is just a fancy word for disorder or randomness. Think about a brand new deck of cards, perfectly ordered by suit and number. That's a state of low entropy. It's highly organized. Now, give it a good shuffle. It becomes a jumbled mess of high entropy. The odds of that deck shuffling itself back into perfect order are astronomically small. It's not impossible, just incredibly improbable. This is the second law of thermodynamics in action. In any closed system, like our universe, total entropy always increases. It's not that some physical law forces it to, simply that there are infinitely more ways for things to be disordered than ordered. This statistical reality is what gives us the thermodynamic arrow of time, the very reason why events unfold from past to future. But this leads to an even bigger mystery. If entropy always increases over time, it means that the universe must have started in an extraordinarily low entropy state at the moment of the Big Bang. But why? The early universe was an incredibly hot, dense soup of energy, which sounds pretty chaotic, right? Well, from a gravitational perspective, it was remarkably smooth and uniform. That uniformity was a state of immense order, not chaos. This special low-entropy beginning is the starting pistol that fired the arrow of time. Without it, the universe might have no direction at all. There'd be no before and after, just a static existence. Cosmologists are still debating why the universe began this way. Was it just a random initial setting? Or does the answer lie in some deeper quantum principle we haven't discovered yet? What we do know is that every single moment of change, from a star being born to you taking your next breath, owes its existence to that initial perfect order. There's also a psychological arrow of time that we all experience. Our brains constantly create and store memories of the past, but we can't remember the future. This isn't just a philosophical quirk. It's a direct consequence of thermodynamics. The act of forming a memory is a physical process. Neurons fire, chemical bonds are rearranged, and your brain consumes energy. All of these actions increase the total entropy of the universe. So, we can only form memories in one direction, because our bodies and our brains are physical systems, bound by the same thermodynamic laws as everything else. When you recall a past event, you are literally embodying the universe's forward march of time. You're not just perceiving time's arrow. You are a part of it. Things get even stranger when we journey into the quantum realm. The main equation of quantum mechanics, the Schrödinger equation, is also time-symmetric. You can run it backward, and the math still works. But here's the twist. The moment we try to measure a quantum system, something irreversible happens. The system collapses from a cloud of possibilities into a single, definite state. This act of measurement seems to introduce a one-way step. Some physicists believe this collapse is what fundamentally creates the arrow of time, that time's direction only emerges when information is recorded and entropy increases through the act of observation itself. But others have a more radical idea. Maybe at the most fundamental level, time doesn't exist at all. Some theories of quantum gravity describe the universe with a single, timeless equation. From that perspective, what we feel as the flow of time is just our consciousness moving through different configurations of a static, unchanging reality. We aren't moving asterisk through asterisk time. We're just one part of its timeless structure. Einstein himself seemed to lean towards this view. In a letter he wrote just before his death, he said, "The distinction between past, present, and future is only a stubbornly persistent illusion." This idea is captured in the block universe model. Imagine all of time past, present, and future laid out at once, like a four-dimensional landscape. Every event that has ever happened, or will ever happen, already coexists in this block of space-time. The past isn't gone, and the future isn't unwritten. It's all there. The reason we perceive time as flowing is simply because our consciousness is traveling along one specific path through this landscape. From the universe's point of view, nothing happens. Everything simply is. It's a profound thought. If this is true, the flow of time isn't a fundamental property of the universe, but a feature of our perception. More recent research offers yet another fascinating possibility, that time isn't fundamental at all, but emerges from quantum entanglement. Entanglement is the strange connection where two or more particles become linked, sharing a single fate, no matter how far apart they are. In this view, time is relational. It's a way of measuring how one part of the universe changes relative to another. The physicist Carlo Rovelli explains that time is unto a universal river flowing at the same rate for everyone. Instead, it's a local network of events and relationships. Your time is slightly different from mine, and both are different from the time experienced near a black hole. If you could zoom out far enough, beyond the scale of galaxies, this familiar flow of time might dissolve completely, leaving only a timeless web of quantum interactions. Time, in this sense, is stitched together by the relationships between things. So, if entropy is what gives time its direction, what happens when entropy can't increase anymore? In the far, far, far distant future, trillions of years from now, our universe is predicted to reach a state called heat death. This is a state of maximum entropy, where all energy is spread out perfectly evenly. Everything will be the same temperature, and no useful work can be done. In that scenario, change itself would cease. With no change, there is no cause and no effect. The arrow of time would simply fade away, its job complete. It wouldn't be that time stops, but that one moment would be utterly indistinguishable from the next. Time would lose its meaning, swallowed by a final, perfect equilibrium. So where does all this leave us? We have a pretty good idea that entropy gives time its forward direction. We know from Einstein that time is flexible and relative, and from quantum mechanics that it's fuzzy and uncertain. But we still don't know what time asterisk is asterisk at its core. Is it a real dimension, just like space? Is it an illusion created by our own consciousness? Or is it an emergent property that arises from the quantum world? The honest answer is, we don't know yet. But the quest to understand it pushes us to the very limits of science, back to the first moment of creation.
Oh.
The mystery of time isn't just a puzzle for physicists. It's a question about the nature of our reality and our place within it. On the cosmic scale of galaxies and black holes, time bends and stretches, a pliable dimension warped by gravity. But here on Earth, time is the quiet, steady rhythm behind everything we do. It's in every heartbeat, every rotation of our planet, every human lifetime. In this video, we're bringing our focus back from the cosmos to the familiar, because long before time became an object of scientific study, it was the very medium through which life unfolded. Here on Earth, time isn't just measured, it's lived. The very existence of life depends on time having a direction. Without it, cause and effect would dissolve. Evolution would be meaningless, growth would have no sequence, and memory would be impossible. Every living thing is a clock, and I mean that literally. Inside your cells, circadian rhythms regulate when genes turn on and when they rest. Plants turn their leaves toward the morning sun, bacteria divide in steady cycles, and animals migrate in sync with the seasons. Time is coded directly into biology. It's not some external concept. It's a property of life itself. These internal clocks trace their roots back to the cosmic rhythms that shaped our planet's environment, the Earth's rotation, its orbit around the sun, the moon's tidal pull. When day and night began alternating on the young Earth billions of years ago, life learned to dance to that pattern. Organisms that could predict the cycle of light and dark gained a huge advantage. So, over eons, biology and planetary motion became perfectly synchronized, an elegant resonance between life and the cosmos. The sun, burning for billions of years, set the tempo for everything we know. Unlike most other species, humans developed more than just biological rhythms. We developed an abstract awareness of time. We remember the past, and we anticipate the future. We plan, we regret, we imagine all of these, are mental acts that depend on projecting ourselves through time. This cognitive leap reshaped civilization entirely. Our ancestors learned to track the stars to predict the seasons. They noticed the cyclical nature of life, planting, harvesting, migration, solstices. From these patterns, the first calendars emerged, tools that turned the sky into a massive clock. Mark time was to gain a sense of control over it. And in that control lay the seeds of agriculture, architecture, religion, and science. Look at ancient monuments. Stonehenge is aligned with the solstices, the pyramids of the Maya with the equinoxes, and Egyptian temples with the rising of the star Sirius. Time became sacred because it was tied directly to survival, order, and a sense of cosmic harmony. But as civilization advanced, our relationship with time began to shift. We went from simply observing it to measuring it with ever-increasing precision. Sundials gave way to water clocks, then to the magnificent mechanical clocks of medieval Europe, and eventually to the hyper-accurate oscillations of quartz crystals and atomic timekeeping. Each improvement brought new layers of accuracy and new consequences. The Industrial Revolution ran on clock time. Factory shifts, train schedules, mass synchronization. Society was no longer governed by the rhythm of the sun, but by the ticking of machines. In a way, humanity entered a new epoch, ruled not by natural time, but by artificial time. And yet, our perception of time remains incredibly elastic. When you're bored, time crawls. When you're completely absorbed in something you love, it vanishes. A single day of anxious waiting can feel longer than a year of pure joy. This isn't just a feeling, it's neurological. Our perception of time is constructed by brain networks that integrate memory, attention, and emotion. Your brain doesn't measure time like a clock. It creates the experience of it. And it's not just us. Different species perceive time differently. Fly, with its faster neural processing, experiences the world in what would seem to us like slow motion. To a giant tortoise, perhaps our world zips by in a blur. So even here on Earth, time isn't a single universal experience. It's a local phenomenon tied to biology and perception. Zooming out, entire civilizations are carried along by the current of time. Empires rise and fall. Languages evolve. Knowledge accumulates. In human history, time became both a record and a tool. Calendars defined the reigns of kings, religions defined cosmic cycles, and historians began to define entire eras. The invention of historical time, the awareness that the past is fundamentally different from the present, changed how humanity saw itself. We began to see stories of progress, of cause and effect, and of destiny playing out across generations. Yet even as we mastered dividing time into seconds, minutes, and centuries, we never escaped its psychological pull. Einstein's relativity tells us that now is subjective, different for every observer. But our human consciousness insists on a shared present, a collective illusion we all agree to live inside. This shared now is what allows civilizations to function, to coordinate, plan, and remember together. It's a social construct built upon the bedrock of physics and perception. On a cosmic scale, all of human time barely registers. If the universe's 13.8 billion year history were compressed into a single calendar year, the entire span of human civilization would appear in the final seconds of December 31st. All of our written history, from ancient Sumer to the internet, would occupy less than the blink of an eye. Yet in that blink, we have learned to manipulate time in astonishing ways. We synchronize atomic clocks down to the nanosecond. We read time written in atoms themselves through radioactive decay to measure the age of rocks and fossils. We even use Einstein's time dilation to make our GPS satellites work correctly. This mastery of time has given us immense power, but it has also brought a new kind of anxiety. We live longer than ever, yet we constantly feel short on time. Our technology accelerates everything, compressing years of change into mere months. Human life, once bound to natural cycles, now races at digital velocity. Time has become not just a dimension, but a commodity. The end. In every story we tell, whether in religion, art, or science, time provides the thread of meaning. Creation myths mirror the flow of the cosmos. The novels we read are built on beginnings, middles, and ends. Even our sense of self depends on temporal continuity, the memory of who we were, and the anticipation of who we might become. Take away time, and identity collapses. Without the past, there is no memory. Without the future, there is no hope. This reveals something profound. For conscious beings like us, time isn't just something we measure. It is existence itself. Every thought, every emotion, every relationship unfolds in time. We don't just live in time. We are time, expressed through matter that has become aware of its own passing. Here on Earth, we learn to count time, then to question it, and now to bend it through physics and technology. But no matter how much we master it, time remains both deeply intimate and impossibly infinite, the most personal and the most universal of all dimensions. The same laws that govern the drift of galaxies also govern the beating of your heart. That connection between cosmic time and human time is what links us to everything that ever was or ever will be. For thousands of years, we saw time as a constant, an invisible river flowing steadily in the background of our universe. But science, through centuries of curiosity and calculation, shattered that simple picture. What we once thought was absolute turned out to be one of the most mysterious and flexible concepts in all of physics. This is the story of how humanity didn't just learn to measure time, but how we learned to bend it. Our modern journey begins in the 17th century with Isaac Newton. He gave us a universe that ran like a perfect machine, a clockwork universe governed by precise, predictable laws. For Newton, time was the ultimate metronome, ticking at the same rate for everyone, everywhere. He called it absolute, true, and mathematical time, a universal stage on which the cosmic play unfolded. This idea was powerful, and for a long time it worked beautifully. It allowed us to predict the orbits of planets and the fall of an apple with incredible accuracy. For centuries, this was our reality. Time was simple, dependable, and the same for all. But as we looked closer, especially at the nature of light, tiny cracks began to appear in this perfect clockwork. By the late 19th century, scientists stumbled upon a puzzle that defied Newtonian physics. They were studying light, and logic suggested that its speed should behave like anything else. If you run towards a thrown ball, it seems to come at you faster. But experiments, most famously the Michelson-Morley experiment in 1887, showed something baffling. The speed of light was constant. It didn't matter if you were moving towards it, away from it, or standing still. Light speed was always the same. This result made no sense in Newton's world. It was a clue that time and space weren't the rigid, separate concepts we thought they were. And then, in 1905, a young patent clerk named Albert Einstein provided the answer, and in doing so, he completely redefined our universe. Einstein's theory of special relativity was a stroke of genius. He started with two simple ideas. The laws of physics are the same for everyone, and the speed of light is constant for everyone. To make both of these true, something had to give. That something was time itself. Einstein showed that time and space are not separate, but are woven together into a single fabric, space-time, and this fabric is flexible. The faster you move through space, the slower you move through time. This isn't a metaphor. Your clock literally ticks slower. Two people moving at different speeds will actually experience time passing at different rates. Time was no longer a universal river. It was a personal stream, its flow depending entirely on your motion. But Einstein wasn't done. 10 years later, in 1915, he unveiled his general theory of relativity, which brought gravity into the picture. He revealed that gravity isn't a force pulling objects together, but a consequence of mass and energy warping the fabric of space-time. Imagine placing a bowling ball on a trampoline. It creates a dip that causes smaller marbles to roll towards it. That's gravity. Massive objects like stars and planets curve space-time around them. And this curvature doesn't just affect space, it affects time. The stronger the gravity, the slower time flows. Time was no longer just a dimension. It was a dynamic, geometric player in the cosmic dance, stretching and squeezing in response to matter and energy. These weren't just abstract ideas. They made real, testable predictions. And the proof came in spectacular fashion. During a solar eclipse in 1919, astronomers observed that starlight passing near the sun was bent, just as Einstein's theory of curved spacetime predicted. Later, incredibly precise atomic clocks were flown on airplanes. When they landed, they were slightly out of sync with clocks on the ground. The flying clocks, moving faster and experiencing weaker gravity, had ticked just a fraction of a second faster. This isn't just a quirky scientific fact. It's essential to our modern lives. The GPS satellites orbiting Earth are moving at high speeds in a weaker gravitational field. If engineers didn't constantly correct their clocks for both special and general relativity, your GPS would be off by about 10 kilometers every single day. Einstein's strange new time is built into the technology you use every day. But just as Einstein was unifying space, time, and gravity, another scientific revolution was brewing, one that would introduce a new, profound weirdness to our understanding of time. This was the world of quantum mechanics. At the subatomic level, physicists like Heisenberg and Schrödinger discovered that reality isn't fixed and certain. It's probabilistic. A particle doesn't have a definite location until you measure it. The universe, at its most fundamental level, seems to operate on chance. This deeply troubled Einstein, who famously said, "God does not play dice." The smooth, continuous, geometric time of relativity seemed completely at odds with the jumpy, uncertain world of quantum physics. This is one of the biggest challenges in science today, finding a way to merge these two descriptions of reality into a single, unified theory of quantum gravity. So, where does that leave us today? Physicists at the cutting edge are exploring an even more radical idea. Maybe time is unfundamental at all, but it's an emergent property, something that arises from a deeper, more basic reality. Much like temperature emerges from the collective motion of atoms, theories with names like loop quantum gravity and string theory imagine that space-time itself is built from tiny, discrete bits of quantum information. In this view, the smooth flow of time that we experience is an illusion, a large-scale effect of countless microscopic events. Black holes, where time slows to a near stop at the event horizon and breaks down completely at the singularity, become theoretical laboratories for testing these ideas. The arrow of time itself, the reason it flows from past to future, might be linked to the flow of information and the inevitable increase of disorder or entropy in the universe.
Yes.
From Newton's absolute clock to Einstein's flexible spacetime, from the uncertainty of the quantum world to the idea of time emerging from pure information, our journey to understand this fundamental concept has been nothing short of extraordinary. We can measure time with atomic precision. We can bend it with speed and gravity, yet we still can't say for sure what it truly is. The more we learn, the more it seems that time isn't just the stage where the universe performs. It is the performance itself, a dynamic, unfolding process of existence. But this raises one final, haunting question. What happens to time in the far, far future, when the stars have all burned out and the universe has expanded into a cold, dark emptiness? What is the ultimate fate of time? We'll explore that final frontier in our next chapter.
Time beginners. Far as we can tell, 13.8 billion years ago, in the very first instant of the Big Bang. But it wasn't born asterisk in asterisk space. It was born asterisk with asterisk space. The two are inseparable, expanding together, stretching the very fabric of the cosmos outward, like a balloon being inflated. It's a mind-bending idea. Before the Big Bang, there was no before. There was no space for time to exist in. But this raises a profound question. If time had a beginning, must it also have an end? This isn't just a late-night philosophical debate. It's a question that strikes at the heart of physics, touching on the ultimate fate of the universe and everything within it. Our stars, our galaxies, our atoms, and even our own fleeting existence. To understand the end of time, we have to journey into the deepest, darkest, most distant future imaginable. Let's start with a scenario physicists call the slow death. It's not dramatic, but it's relentless. As the universe continues its endless expansion, everything thins out. The vibrant energy that fuels the cosmos today becomes diluted across vast empty distances. Galaxies drift farther and farther apart, becoming lonely islands in an ever-growing ocean of nothingness. Stars, the brilliant campfires of the cosmos, have a finite amount of fuel. They shine brightly for billions, sometimes trillions of years, but eventually they all go out. They fade into cold, dim remnants, white dwarfs, neutron stars, or the silent gravitational traps of black holes. After trillions upon trillions of years, the last star will be born, and the last light from star formation will fade. The universe will enter what scientists call the degenerate era. Imagine a cosmos that is almost completely dark, unimaginably cold, and silent. The last faint embers of matter are slowly cooling toward absolute zero, the coldest temperature possible, where all atomic motion nearly ceases. At this point, time, as we understand it, begins to lose all meaning. For time to be felt, for it to be measured, something has to happen. Light has to flicker, atoms have to vibrate, planets have to orbit stars. Change is the engine of time. But when everything in the universe reaches the same temperature, a state of perfect equilibrium, what is there to change? Entropy, the scientific measure of disorder, will have reached its absolute maximum. The cosmos will fall into a state known as heat death. It's a silent, static equilibrium where no work can be done, no energy can flow, and no events can occur. To any conscious observer, if one could possibly still exist in such a barren wasteland, it would feel as though time itself had simply stopped. But some theories paint an even stranger, more dramatic picture of the end. Einstein's revolutionary equations of general relativity, when projected into the far future, can describe a universe that doesn't just expand, but expands faster and faster and faster. This accelerated expansion is driven by a mysterious force we call dark energy. We don't know what it is, but we see its effects everywhere. It's pushing the universe apart. If this acceleration continues, something truly bizarre will happen. Distant galaxies will eventually be pushed away from us faster than the speed of light. Now, you might think nothing can go faster than light. And you're right, nothing can travel through space faster than light. But this is space itself, expanding, carrying the galaxies along with it. They won't be moving. The distance between us will just be growing at an impossible rate. One by one, they will cross a cosmic horizon and vanish from our view, their light no longer able to reach us. Forever, eventually, our own local group of galaxies will be all that remains. Visible, single, lonely island in an endless, infinite ocean of blackness. The rest of the universe will be gone, hidden behind a curtain of space-time we can never peek behind. Fast forward 100 trillion years, and the last dim red dwarf stars finally burn out. The degenerate era begins. But it gets even weirder. Over periods of time so vast they defy human comprehension, think 10 to the power of 40 years even, the mighty black holes will evaporate, bleeding away their mass through a process called Hawking radiation. Beyond that lies the so-called dark era. All that's left is a sparse, cold soup of scattered photons and elementary particles, drifting aimlessly through an empty void for eternity. But what if the acceleration doesn't just stop there? A more violent scenario, known as the Big Rip, suggests that the expansion could become infinitely fast. In this future, the repulsive force of dark energy would become so strong that it would overwhelm everything else. First, it would tear galaxies apart, then solar systems, then planets and stars. In the final moments, it would be strong enough to overcome the forces holding atoms together, ripping them apart. And in the very last fraction of a second, space-time itself, the fabric of reality, would be torn to shreds. In either case, the result is the same: a cosmos with no clocks, no cycles, no events. Time, as a measurable sequence of change, would effectively end. And yet, physics seems to have a problem with absolute endings. It feels unnatural. Some cosmologists believe that the end of time might just be an illusion, a limitation of our current understanding. They suggest that even in the cold, dead state of heat death, something new could emerge. Quantum mechanics, the weird and wonderful science of the very small, tells us that even in a perfect vacuum, there are tiny, random fluctuations particles popping in and out of existence for fleeting moments. What if, over an almost infinite timescale, a random quantum fluctuation could be large enough to trigger something incredible? Like the birth of a new Big Bang, a rebirth of space-time itself. This idea is called the cosmic bounce. It suggests that our universe might not be a one-time event, but part of an eternal, cyclical chain. Each universe expands, cools, and dies, only to give rise to a new one from its ashes. A cosmic phoenix, endlessly reborn. If that's true, then time never truly ends. It simply renews, folding into itself like waves upon an infinite cosmic ocean. Other theories go even deeper, questioning the very nature of time itself. What if what we perceive as the flow of time is not a fundamental feature of reality at all, but just a property of how we, as conscious beings, observe it? In some cutting-edge interpretations of quantum gravity, there is no universal clock. The universe simply is a static, four-dimensional block in which every single moment, past, present, and future, already exists simultaneously. Think of it like a movie reel. Every frame of the movie already exists on the film. Our experience of the movie's story, of its flow, is just our consciousness moving from one frame to the next. In this view, what we call time is just our path through this vast, pre-existing configuration of all possible moments. The universe never begins and it never ends. It just is. And yet, for all this cosmic speculation, we are creatures of time. Our entire lives are defined by it. Our memories of the past, our hopes for the future, our very identities, they all rely on the arrow of time pointing forward. We can't escape its current. We can only try to measure its passage. To imagine a universe without time is to imagine existence without experience, reality stripped of sequence, of story, of meaning. And maybe that's why the concept of time fascinates us so deeply. It is both our greatest mystery and our most intimate companion. It is the rhythm by which we live, love, create, and eventually fade away. Every heartbeat, every sunrise, every breath we take is a small, beautiful act of defiance against the silent, cold eternity that awaits. So when the last light in the universe finally fades and the great cosmic clock winds down, perhaps time won't truly disappear. Perhaps it will simply transform into something beyond our current perception, beyond our equations, beyond our wildest imagination. And perhaps in that final transformation lies the truest expression of the universe's beauty, that even as everything ends, something, somewhere, somehow begins again. Time is not the enemy of eternity. It is its expression, the whisper of infinity made visible. We are not trapped in its flow. We are its witnesses brief, brilliant sparks in an endless, unfolding story. that, as our universe expands into the darkness, our understanding of time continues to expand with it outward onward, toward that infinite horizon where physics meets poetry. The question is not just what time is, but what we are within it.